Hello everyone, today let's solve the problem number 191, number of 1 bits. So, what the question states here, we have been given a positive integer n, you can clearly see here, we have been given a positive integer n, we have to return the number of ones, means here what we need to do, we have to count the number of digits, number of ones basically. First, ones means set bits and its binary representation. So here we have to return the number of ones in its binary representation, also known as Hamming byte. First, we need to convert this one to the binary number or the binary this one representation. Then we have to count the number of ones that is present in the binary representation of the particular number n, right? That they have given here. So let's come to the first example here. In this case, n we have 11. So how we got 3 here? In this case, 1011 we have in the binary representation. The binary representation of 11 is 1011, right? So here in this case 1011, when we count this one, we have to count the number of ones and return it, right? So here in this case we have 3 ones. So the output is quite obviously 3 here, right? So let's come to the second example here. N we have 128. So this is the binary representation of it, and we have only one here, right? So the count of 1 is only 1. We will return the output as 1 here in this case, right? So I hope first two examples are completely clear. Let's move on with the third edge case here. N equals 2147 483645 we have. So the number of ones we have here is this is the binary representation of the number, this one, right? So the number of ones we have here is 30. So the output is quite obviously 30 here in this case, right? So the output we need to return here as 30 in this case. Right, I hope the question is completely clear. What we need to do is completely clear as well. Easy to understand, right? So let's discuss the approach first, followed by the edge cases one by one, and then finally write the code and discuss the complexities for the code that we have written. Initially, let's discuss the approach first. So the first thing that we need to keep, the first thing that we note down here is we'll be going with the Brian Kernighan's bit manipulation algorithm, right? So this is the approach that we'll be basically going with. Just keep this in mind. We are going with the so I have considered the same first example that they have given in the question. So n equals 11 we have been given. So the binary representation of 11 is 1011, and we have to return the count of 1. So we have 3 ones in its binary representation, so we'll return 3 as output. So this is fine. Let's move on with the step-by-step execution here. N equals 11, same the first example that I've considered here. So here, as we are going with the Brian Kernighan's algorithm, each operation n, this is nothing but the bitwise end. Just keep this in mind. So this is bitwise end, right? And equals whatever I have written here, it equals n minus 1 is nothing but the previous number. Basically each operation, n means 11, means n minus 1 is 10. So in that case itself we will be comparing. So each operation turns off the rightmost set bit, nothing but 1. So in this case, first n equals 11, we have binary representation of 11 is 1011, count is initially 0, right? Count is 0. So first step, main step here is, let's come to the second step or the first main step here. N equals 1011, and we will compare with the previous number, right? N and n minus 1. N minus 1 is nothing but in this case the previous number. I have already said this one. We are going with the Brian Kernighan's algorithm. Means suppose n has been given 11, we will compare with the previous number 10 in this case. So 10, both we will convert to binary representation of this, and then we'll go with a bitwise AND. This is nothing but the bitwise AND, right? AND equals whatever I have written. Bitwise AND, what it states basically, when we have 2 ones, then only we will get the output 1, right? 0 1 will lead to 0, 1 0 will also lead to 0, 0 0 will also lead to 0, only 1 1 will lead to 1. Just keep this in mind. We are going with a bitwise, we are performing the bitwise AND, and we are going with n and n minus 1. N equals is bitwise and n bitwise and n minus 1 means the current number and the previous number. So just keep this in mind. This is Brian Kernighan's algorithm. So here in this case 1011 for 11, 1010 for 10. So the count here is 1. So the count, the 0, whatever 1 we have converted to 0, right? So in this case here 1011. So this will be 1011 and 1010, right? So here we have only 1, right? So the count is quite obviously 1. Sorry, I got confused here. So let's move on with the third step here. Now we have 1010, and the previous one 1010 is nothing but, in this case, 9, and we will be going with the previous number, nothing but 8 here. This will be 1001, 1010, and 1001 here. This will be 0001. So again one more 1 we have here. The count, we will increase the count to 2. So this will be 1010. Again I'm telling you, if it is not visible, 1001. So this will be 1, this will be 0 basically, right? Only 1 will lead to 1 bitwise AND. So here in this case we will increment the count as we have one more 1, right? So count is 2. So now we have 1000, and we'll go with this one, 0111, right? We'll go with 0111. So now when we perform bitwise AND operation, this will be 0111. So here in this case, so this one, now we have at last we have to get all the zeros, right? So when we got all the zeros, we will increment the count to 3, last step. So this we will be doing basically. Then the count we have got is 3. So the final output will be returning the same value. The final output that we got here is 3, which is equivalent to the output that they have given for the first example in the question. So the approach works absolutely correct in this case. As approach works absolutely correct, or as we are completely familiar with the approach, let's discuss the edge cases one by one. So the first edge case here, this is for the this one, single bit set, right? So we are going with a single bit set, means n equals 1 we have. So here this is not 11 basically, this is just 1. So output is quite obviously 1. Only 1 bit set and binary. This will be output will be 1 itself. So next edge case is for the all bits 0. When I say all bits is 0, we have n equals 0 here in this case, right? So no set bits and binary. This will be 0 itself. Output will be 0 itself. Let's move on with the third edge case here. Only 1 and higher bit. So n we have 2 here in this case. N we have 2 here in this case. So the binary will be in the binary form, it will be 1 0. So the output will be quite obviously 1 itself, right? Only 1 we have. Let's move on with the fourth edge case here, consecutive set bits. So 7 here. We have got n equals 7, right? So 7 is represented 1 1 1 and binary. So here in this case the output is quite obviously 3, right? 3 ones, the count of ones is 3, right? So the output will be 3. So let's come to the fifth edge case here. In this case we have already discussed this one in the question. Basically they have given this one in the question itself, right? The last example. So 2147483647 we have. So the output that we got here is 31. So I don't have to, in the binary representation we have this one, 31 ones. So you can just go through the example 3 for the binary representation if you want to count, right? So these are the 5 edge cases that we need to keep in mind, right? So the first edge case is for the single bit set, the second edge case is for the all bit 0, the third edge case is for the only 1 1 in the higher bit, the fourth edge case is for the consecutive set bits, and the fifth edge case is for all the bits set on 32-bit int. So the output is quite obviously 31 in this case, right? So the output is quite obviously 31. So for this one, this particular one. So these are the 5 edge cases that we need to keep in mind. So now we are completely familiar with the edge cases as well as the approach, right? So as we are completely familiar with the edge cases and approach, we are good to write the code. Let's start writing the code. So here the first thing is we have to initialize a counter to keep track of the set bits, right? So I'll just go with the count itself here in this case. I'll just initialize this one to 0. This is fine. So the next step here is we have to loop until all the bits are 0, right? So we have already seen this one in the approach. I have clearly explained this one. When we have the last count we will be incrementing is when all the bits are converted to 0 basically. So I'll just go with while n not equal to 0, right? So here we performed this operation. If you remember this one, what do you call this is basically Brian-Kernighan's algorithm, right? We are going with a n bitwise and n minus 1 basically. This one, let me give this one in the bracket. So this is fine. So the next step here, this is we have to increment the count for each set bit that is being removed. So I'll just go with means whatever this one, if we have 1, we will convert that one to the 0, right? Every time. So 1 bit that is being removed, when 1 bit we are removing, at that point of time we will be incrementing the count by 1. Means we are incrementing the count for each bit set that is being removed. So the final step here is we will return the total number of set bits that is found. So I'll just go with return count. So this is it for the code. Let me format the code once and let me hit the run button. So you can clearly see here the sample test cases are getting passed. Means the code works absolutely correct on this case, right? So here let me hit the submit button quickly. So I hope this works for all the test cases, man. Let's see. So here you can clearly see all the test cases are getting passed. Means the code works absolutely correct on this case. So let's quickly discuss the complexities for the code that we have written, right? So the approach that we went with here is this one, Brian Kernighan's bit manipulation algorithm. We know this one. So the what would be the overall time complexity here? Overall time complexity would be big O of k, right? What is k here? K is nothing but the number of set bits and n. So as we are or as the loop runs only for the number of set bits, the time complexity or the overall time complexity would be big O of k. So what would be the space complexity here? The space complexity would be big O of 1. So why it is big O of 1 here in this case? Because we are only making use of the constant extra variables, nothing but count and n. So you can clearly see here count and n. This we are speaking of, right? This one. So overall space complexity would be quite obviously big O of 1. So the time complexity and the space complexity for the code that we have written is big O of k and big O of 1. I hope the complexities are completely clear, and I hope whatever the code that we have written is completely clear as well. For now, this is it. Thanks for watching, guys.